Howdy, everybody. We're here for day 12 of Advent of Code. This one was a pretty interesting one. I found it fun. I think you'd consider it a dynamic programming solution. So if you're familiar with that, you could kind of work your way around it. But dynamic programming as a general idea may seem easy, but like actually implementing it for a problem can be a little tough. And I'll show you my gotchas and stuff like that I had while I was solving it. So let's just get into it. First, let's look at the problem here for day 12. The general idea is you're given a set of records for springs, and you're trying to determine which springs are damaged or undamaged. And it turns out that they don't know. There's some of them that they actually don't know their state, if they're damaged or undamaged. And so they want you to try and figure out how many possible solutions there are to that, to create like a valid set of states. It'll make a little bit more sense in a second, but the idea is you have some that are working, some that are not, and then some that you don't know. And they happen to keep a little bit like, if you could think about it as a checksum of it, so you can verify which ones are damaged or undamaged. So if you look down here, there's one damaged, and then 3 damaged. That checksum is 113. So it works like that. Same thing with here. This is also 113. You have 1 damaged, 3 damaged. The idea is these numbers are just groupings of damaged. So there's little groups for that are damaged for each of those numbers. So like when you get down here, a group of 3 would translate to 3, a group of 2 would translate to 2, and a group of 1 would translate to a 1. So that would mean like this is a valid solution. Where you get to the issue is now there's like some unknown values, something you don't know if they're damaged or not. Like the records aren't clear on whether or not they are damaged. And so the question is, how many valid solutions, how many different arrangements could you make from that, right? So for example, these question marks, you don't know if they're valid or if they're working or damaged. Operational or damaged, I guess, is what they used. So you have to figure out how many ways from this string can you make this set of damaged groups. And so if you think about it, in this case, the only way to do it is if this one was damaged and this one was damaged, because that would create 1, 1, 3, and then this one would not be damaged, right? It would be operational. That's the only way you could do this. If you tried to go 1, 1, and not damaged, you would get a 2 here instead of a 3. So down here, you could see like the only place you could place this last value 3 is right here. It has to be right here. This is the only place you could put it. So then the question is, where do you place these ones? And you can kind of reason about this in your head, right? As you can say like, oh, well, I could place one here and here, or I could place one here and here, or I could place one here and here, or I could place one here and here. So in that case, there's like 4 ways for you to do these 1-1s in this group. But the 3 always has to go down here, right? So the number of valid solutions for this one is 4. Let me make sure I'm not speaking incorrectly. Yeah, it's 4, right? So again, the way to think about this is you're gonna kind of, or the approach you're going to take in your mind is trying to fit pieces in places, right? When you're just doing it. And you can kind of do that in your head, right? Is you can say, oh, the 5 goes here, the 6 goes here, and so the 1 could go in any 4 of these places, which means there's 4 valid solutions. Sometimes they get harder, like this one is substantially harder. Notably, the 3 can't go right here because there's a damaged one here, so that would actually make a 4. So the 3 must go here, and then you say to yourself, okay, well now this one can't be damaged, otherwise it would be included in this count of 3. So I just need to calculate, how do I get 2 and 1 from these positions right here that I don't know about. And they actually iterate over all of them, right? You can go 2 space 1 to 2 spaces 1, and you kind of go through all of these and slowly slide over the 2 and the 1, or you slowly slide over the 1 for each 2 position, and then you move the 2 a little bit and then slide it over, and you go through all those places to get all the valid ways that you could make that 2 and 1 from that group, right? So when you count all these up, it turns out, given this record of springs and this number of groupings for damaged springs, you could create 10 different iterations or 10 different versions from those question marks. I hope I explained that well. And so the question they're asking is, if you go through each record, so if this one has 1, this one has 4, this one has 1, 1, 4, and 10. If you sum them all up, how many total arrangements can you make from all of the springs? And that is 21. Okay, so that's the problem at like a really high level. I just want to take a minute to, sorry if you're in the dark, this is a little bright. What it initially reminded me of were these nonograms. I don't know if you've ever done these before, but this is a relatively simple one. The idea is you have like these digits and these numbers. Maybe it'll look better in like a 10. And you can see there's some arrangement, for example, of 4 and 1 here, which means there has to be 4 connected and then 1 somewhere else in the list, right? But it doesn't have to be 4 and then some numbers and then 1. It could be anything, right? So it could be anywhere in that thing. In this nonogram, though, for example, it has to have a 1 followed by 3, and there has to be a space in between it. Because there's only 5, you actually know that it has to look like this, right? It has to look like this, and this one can't be 1. Another thing you can do with these nonograms is you can say, oh, if there's 3 and the total is 5, I know that like my lower bound, say I go this way, would include this one, and my upper bound going this way would include this one. So I know that for this 3, any solution has to include this middle thing. Anyway, solving this problem actually made me think a little bit about nonograms. As I was learning about these nonograms, I'm like, oh, it'd be interesting if there was sort of a solver that could solve these nonograms. And I bet you if there is, it uses some kind of dynamic programming solution similar to this, right? It's going to go through all the valid iterations for each of these each of these columns and all the valid solutions for each of these rows and kind of do an intersection of them, right? And say, oh, here's the only way that I can put these two together, something along those lines. Anyway, if you know a lot about nonograms or you've done some programming for them, I'd definitely be interested to hear how you solve that. But back to the problem, this is probably the easiest way to think about this is through a recursive approach. And I'll do it at a really high level. If you were listening before, I already kind of did it recursively, right? I was already kind of saying, oh, well, what if I place it here and then check and stuff like that, right? So that's essentially what the recursive solution is. And in a dynamic programming world, recursion is part of dynamic programming. But one of the key features is actually memoization, or keeping track of like previous answers, and that greatly reduces your sample set. And we'll talk about that in a little bit. But if you're not familiar at all with dynamic programming and you want to try and solve some problems using dynamic programming, you can search online. I went recently, maybe a year or so ago, through this dynamic programming course on LeetCode. It's called a study plan. I'll try and remember to include the link. But the idea is they have a bunch of problems that you try and solve with dynamic programming, and the idea being it'll kind of help you understand the nature of dynamic programming. At a high level, though, what you're doing with dynamic programming is saying, can I decompose a larger problem into smaller problems, and then just do some kind of operation on the sum of the smaller problems, for example. So in this case, the way to think about it is, for this problem, you can say, if I put the 3 here in this position, then I only actually have to solve for the number of ways that I could put 2 and 1 in this position, like I had said before, right? And then you can do that recursively. You can say, if I put the 2 here, now I only need to solve for the need to find the number of ways that I could put 1 in these positions. And you just do that recursively. And so again, the idea is for dynamic programming is, can I break a larger problem into smaller problems, into a smaller problem for a subset of the issue or of the problem. Some people call it divide and conquer, some other things like that, but that's the general idea. And so recursion is one way to solve it. You can also have a table where you track previous values, and then you know if you have previous values that you can reuse those values. But again, the idea is, if I put the 3 here, and then how do I solve 2, 1 for the rest of this string? And that's what the rest of this is, right? And then you say, if I put 2 here, how do I solve 1 for the rest of that string? And that's these 4 right here, right? And then you ask the next problem, well, what if I put 2 here? How do I solve for the 1 for the rest of the problem, which is these right here? And you just kind of do that recursively and iteratively, breaking the bigger problem into smaller pieces to solve the problem. So when you're doing dynamic programming, the things you want to keep track of are, like, what is the state? How do I know if I've solved the problem or if I haven't solved the problem? Like, how do I know if I've come to a solution? And that needs to be able to, like, trickle back up, right? And then the other thing you need to know is how many solutions did I have, or sorry, how should I say this? How do I break up my solution into those smaller pieces? So those are the two things I want to think about with this problem, is to say, how do I break up this puzzle into smaller pieces? And then how do I keep track of, how do I know when I get to a point where I've got a valid solution and bubble that up? So when you're thinking about how to break this problem up, this one seemed to lend itself to, oh, well, what if I just start here and see how many solutions I have recursively, and then start here and see how many I have. And if there's ever a point where I happen to be able to use a number, I'm going to check how many solutions I have if I use that number, but I'm also going to check how many solutions I have if I don't use that number. And so, for example, you can think about the way you break up the problem into smaller pieces is you say, well, the way that I solve this whole problem is just to say, okay, can I get 3, 2, 1 from here? No, I can't. From here. Can I get 3, 2, 1 from here? No, I can't. And you kind of bubble that up. And eventually you say, well, can I get 3, 2, 1 from here? And you're like, oh, potentially I could get the 3 from here. So now I just need, if I use the 3 here, how many solutions do I have? But also, if I don't use the 3 here, how many solutions do I have, right? So for example, if this was not a hash, I know I have to use the 3 in this case, and I'll show you that in the code. But if I didn't, say this was a question mark, the next question would be, well, what if I put the 3 here? Could I then use the 2s here? Something along those lines. I hope maybe I'm explaining this a lot, but the general idea is, can you take a problem and decompose it into a bunch of smaller problems? And then all you have to do is solve those smaller problems. And those smaller problems are generally easier to solve the more and more you decompose, right? So, and then once you've made all these really small problems, you just kind of bubble up the answers to each of those problems to get your total. So let's look at what that looks like in code. First, let's talk about the parsing. I still used nom for this. I don't think you needed to, but I have an enum for the spring and the 3 different types, right? It's either operational, damaged, or unknown, and that's, a dot, a hash for damaged, or a question mark for unknown. But if it's not one of these two, we assume it's unknown. And then I have a record, right? And within that record, I have the springs. So a value for each of these, right? So that's this chunk right here. And then I have the groups, which are these values right here, right? So how do I create that record? Well, it's just when I'm parsing each of the lines, I just do mini one of any of these, and then a space, and then a separated list by comma of digits. And so that's like your nom part of it, where you're using nom to like parse it. And eventually what you end up is a vector of springs and a vector of groups, those group values that you want. So based on that record, we can then do some iterations over all of them, right? So that's what the main function does, is I just get the input. I call parse all for each of those. So I get a vector of records. I get a bunch of records for my whole input. And then I use a hash map for my memo, which we'll talk about for a second. I do some timing, but then I just call for each of the records in here. I call what are the total number of possible solutions, and I sum all those up, right? So I'm just using an iterative approach, functional approach here to say, hey, for all of the records, calculate the possible solutions and sum them up, and that will give me my solution. We'll talk about some of those other variables in a minute. So then the question is, what does that possible solution look like? And let's go there. That's this part right here. So what does my possible solution take? First of all, it takes that memo function. If you're not familiar with memoization, it's just a way for you to keep track of previous answers, right? So basically what I say is, if I've already solved the problem for a given record, and I know that size, right? If I've already solved the problem for a record that I have, I can just return that value. And that's what this is right here, right? So if I do a get on the memo and there's something there, I get a hit, I know that I can just return that value. I've already solved that smaller problem. And why this is important is, if you think about how you're decomposing into smaller subproblems, like one big problem becomes 2 becomes 4 becomes 8, whatever, it keeps growing, right? And now you get these, you get maybe like a million of them. Many of them down on the bottom are going to be the same, right? Imagine a case where you have no records, like you finish the whole string, and you have no counts, no groups that you're counting. That we already know that solution is 1. There's no need for us to pick it again. But that also bubbles up, right? If you're digging through all of those things, and over here you've already solved for example, if you've already solved for this portion right here or whatever, it's a little hard to show in this case, but if you've already solved for all of these, if you've already solved for this one right here, maybe what I should say, if you've already solved for this piece right here, and you happen to get it later in your iterations, you don't have to solve for it again, right? If you see this string and the number 2, 1, you already know the answer is yes. And so you can solve for it, right? Is the way to think about it. So that's just the way memo works. Is there in Python, you can just you do an @cache right here, and that's essentially memoization. Other languages have the ability to memo. I actually think there's a memo package that someone has created for Rust. I just haven't tried to use it yet. So what do we do in Rust? We just include for each time we recurse, we include the memo with the ability to look it up and set it once we know the value. So that's what the memo is. Otherwise, now we have a record, and we want to start thinking about how do we decompose it. But before we decompose it, we want to think about what are our sentinel cases, right? So that's what these first things are, right? So if I have a record that has no groups in it, so it's an empty list, meaning I've found all the groups in a previous part of the recursion, then I know that I have a valid solution if I don't have any more damaged springs left. And that's essentially what this part is checking right here. We say, If the record group is empty, and I don't have any more damaged springs, then I know I have a valid solution. If my record group is empty, but I do have some damaged springs, then I know this isn't a valid one, right? Like if I got to the end of the list right here, and I still had, if I had something that looked like this, for example, but no groups left, I know it's not valid because there should be at least one more group left, right? There should be one more of these groups left. So that's the way that this one works. Is I say, hey, if there's no groups left, then we're at the end of where we need to check. We just need to determine if there's any damaged springs left, and that will determine if we found a valid solution or an invalid solution. And again, here we insert that record so we don't have to check it again, right? Like if we ever get to this state again, we don't have to check again. It will catch it up here, and it short circuits all of this logic. The logic short circuiting here isn't a huge deal because this is a relatively simple check, but when you're recursing deep, it may become the case. Okay, so we kind of do the same thing here. Is we say at this point we know we have some number of groups left, but we don't know, but we want to check to make sure like we can fill with whatever we have left with the springs, we can fill those groups, right? And that's just a simple length case, right? So if the number of springs is less than the sum of the groups, then we know we can't solve it, right? So for example, if the sum of the groups here is 6, and we know we're like at this position, we know we can't solve it, right? Because we could never go 1, 2, 3, space 1, 2, space 1, right? Like we could never like find that solution. So that's what this check is just doing. These are our like sentinel cases where we say, hey, at this point, I want to just check some base cases. If I have an empty set of groups, I'm done. If I don't have enough space or if I don't have enough springs to fill up my groups, then I'm also done, right? I obviously can't solve it there. And so in that case, I return 0. Okay, so then you start thinking about, well, how do I determine whether or not I can use the position I'm currently in? And the way to think about that is if we go up to one of these like this one right here, for example, the first thing we want to do is check our current spring, like the very next spring that we're looking at. And if it's a dot, like in this example right here, that doesn't actually help us solve the problem, right? The problem is only interested in damaged or unknown springs. If we know the spring works, then it doesn't change our valid solutions. So we can just skip it, right? If we know our current one is operational, we just skip it. And how do we do that? We just recursively call it again, but we ignore, right? So this in Rust is saying like create a list of springs that don't include the first element. So again, we recursively call possible solutions, ignoring that first one. And then once we get that solution, we can memoize it and return that solution, right? So if we're down in the pipe somewhere deep, we're down in like the dynamic programming really deep, maybe we found a spring. We know we don't have to a position. We don't have to test it again. Okay, so now we've kind of done all of like the sentinel cases where we say like, hey, here's some parts where we can just simply return a value, right? It's either valid or not valid, or we don't need to worry about it and we can keep testing. So at this point, we now want to determine if we can place our current grouping at our current position, right? And so the way to think about this is if you're like right here for, let's say you're, I don't know, where would be a good one to show you? If you're right here, for example, you're asking the question, what you're asking now is, hey, can I place this group of 3 here, right? You've already done all the checks and you know you're at a position where you could potentially place the solution, a grouping. And so you ask yourself, well, can I place 3 damaged ones here? Can I put 3 damaged ones here? And in this case, you cannot, because there's a damaged one right after it, right? So if you placed the 3 here, it would actually be a 4, which would cause it to be invalid. Maybe another example, though, is if you're right here, the question is, could you place the 3 here? And the answer is yes, right? You could place 3 here, and then this one would become a dot, meaning it has to be undamaged, and then you could test the rest of the string here. So that's the next thing, is basically what we're asking is, given my current position, can I put the current group in that place? And so I have some kind of like helper things here. I use cur helper variables as the current record group, right? So this is the number. So in this case, it would be 3. And then I want to test if all of the values within the record group are non-operational, right? So this is a simple way to test that. We basically say go through all of the values in that spring and make sure they're not operational. And if they're all non-operational, then that means I could potentially place it here, right? That check is kind of along the lines of right here, I would check these 3 and say, hey, are they all non-operational? In this case, they're damaged, so that's a potential. If I was right here, for example, that would also return true, right? Because these could all potentially be damaged springs, and so I could place a 3 here. If I was in, say, this position right here, and I was looking for 4, for example, I know I can't do that right here because these 3 are operational, so I could never put 4 in there. So the answer to that question would be no, right? And that's essentially what this code is doing here. Then I have another helper function that it says, hey, get me to the end of my current group. And that happens to be the cur plus 1, or the minimum of cur plus 1, which is my current group plus 1, or springs laying. And this is just a check for, there's some cases that I had to I had some bugs at first that actually led me to use this. The idea was, assume this dot is not here. Okay, so then I can always place the 5 here, right? Whether this is a dot, or sorry, I can place the 5 here if this is a dot or it doesn't exist. I hope that makes sense. The idea is I want to, if I place a 6 here, for example, I have to have a dot or be at the end of the string. If there's another hash here, I know I can't place it there because I am out of bound, or I would create a longer string of damaged parts than I have, right? It would be 7 instead of 6. And so in order to check for that, you do a little logic down here, which is a little complicated. But once you've done it, you either want to move to the position after this right here. Like, say I know this is the 6, and then I know this one has to be undamaged. I now want to move to this position. But if I'm off the end of the string, that's actually not helpful, right? Maybe the good way would be this one right here, right? Is if I'm trying to get this one right here, I don't want to move past the end of my string. That would be an out of bounds error, right? So that's just what this end checking is doing. I'm sorry if that was a little complicated explanation, but the reason behind it is I want to make sure that the actual if check that I'm doing here is make sure all of them are non-operational, and then check that the next spring, or the next spring is undamaged, or that I'm at the end of the string. That's what this and this does, right? It says, check that the next spring is undamaged, or that I'm at the end of the string, and so there's nothing after it. In either of those cases, I would be able to place it, right? And the end just helps with that because I can say here is like once I've solved for that piece of it, I can just call it recursively on the rest of it to get the number of solutions for the rest of the piece, right? And I just use end here. Again, to I know I went deep there, but the idea here is at this point, we now know we potentially have solutions. And those solutions, we potentially have a place where we can place a group. And now we need to determine if we can validly place a group there. And so all of this checking is essentially just doing that. Is saying, is this the place that we can place the group? And if it is, then we place it and check for all possible solutions after that. So the answer to that question is, if we place it there, how do we check all the possible solutions, finding the subset, right? Which is the springs are now all but the ones that we've picked, right? So if we're on this one right here and we place the 3 right here, we now want to go to here and check 2, 1, right? So that's essentially what this part is doing right here, right? Is take this, maybe I can show it to you. We start with this, and we call on this right here, right? So you can see we're just calling on the pieces that that we haven't used yet, right? The idea, and this is the breaking it in pieces part, right? Is if we found a position, we can now break this off, and now we just have to solve a sub-problem. Can we find 2, 1 in this group? Well, it turns out you can, but you know, that's what this thing is. Now go check and see if you can solve it with the rest of these. So any of those that we can solve would go into our solution count. So we just say if we can place it there, then we know we have a potential for a valid solution. So we know that at least part of our solution is the possible solutions of the rest. There's one other piece here, though, that you have to think about is, okay, but what if I don't do it there? And that's what this last part is, right? If your current position is unknown, you now know that you could potentially, it could actually be a dot as opposed to a hash, right? And so you say, well, if it's an unknown, I don't necessarily have to use these solutions up here to solve the problem. Maybe this part up here will give me some solutions, but I could also get other solutions by not solving it here. And the way to think about that is a little bit tough. Is maybe I can show you a case here. Imagine you're working on this one again, but instead of working on this, you're working on this problem right here, right? When you're doing the top part, you might say, oh, well, I can, how do I do this? If you're doing the above case, you might say, let's say you're right here, right? You might say, oh, I can put, right here. I can put 2 right here. And so I'm going to test, can you solve the problem by putting 2 there, right? And so that above, you might end up calling something like this. Like this. But you can also ask yourself, well, what if I don't solve it right here? So below here, you actually say, what if I don't use that as the solution and I just move on? What if I just check to see here? This also has valid solutions, right? You can put the 2 here and the 1 here, so you need to account for those as well. This is like, I call it branching, I think, in my thing. The idea is I'm at this point now I can branch, right? I know I can use the solution, but do I need to use the solution here? And so I'm going to branch in both places. How many solutions do I get if I use the solution, or if I do put the group right here, versus how many solutions do I get if I don't put the grouping there? And then the answer to the total number of solutions is just the sum of those, right? So what does that look like in code? Again, up here, I've already counted the number of solutions if we did use the group. So now I just need to count the number of solutions if we didn't use the group, which is down here. And then that's the total number of solutions, right? Okay, we went really deep there, But if you reread through the code, I'll have the link in the description below. If you look at it again, what you're basically just saying at a high level is, see if we've already calculated this subset of the problem, and if we have, we can just return it. And then the next thing we want to check are some sentinel cases, right? Do I have any groups left? If I don't, then I either have a solution or I don't, because I can't go any further. The same thing for springs, right? If there's not enough springs to account for the groups I have left, clearly there's no valid solution. And then we say, okay, if our next spring is operational, it actually doesn't help us add more solutions, so we can skip it. Then we say, if we can place our current group in this current position, how many solutions do we get from that? And then we also ask, what if we don't place it there? How many can we get from that? And once we have both of those, we can add those together, and that is the total solution. So again, you're decomposing the part into smaller problems. And this is the idea of dynamic programming, is you say, hey, I'm going to break this larger problem into smaller problems, and I'm going to track my solutions and kind of, in this case, add them up, right? Sometimes in dynamic programming, you're finding like the best case or whatever, and so you just pick like the min or the max. But in this case, we want the total, and so we're summing all those problems up, right? And they kind of boil up and sum. And so that is how you solve part one. So part two actually doesn't change the solution much unless you were using a very naive approach. If you were just saying, oh, I'm going to brute force look through all of the problems, you would then struggle at that point, because what part two says is, well, it turns out the records were folded up and you actually need to unfold the records. And the way you do that is you basically quintuple, is that what the number is? Quintuple each of the strings and each of the values, joining the strings with a question mark. So this and this becomes this and this, basically making your strings and your groups 5 times bigger. The problem you get though is your solution, that you're trying to solve, doesn't become just 5 times bigger. It's like you have to do exponentially 5 more checks, if that makes sense. It probably doesn't. And it's probably not completely accurate, but it's somewhere along those lines, because now for each iteration you go deep, you may have to iterate over that check a bunch of times. So if you've done a very brute force approach of, I'm just going to try it here and see if it solves it, try it here. Basically, the brute force approach would be like, turn this on, see if it's solved. Turn this on and this off and see if it's solved. And you basically do all of the cases for all the question marks. That would take you forever now, because this is just really huge now. And so the number of solutions becomes substantially larger. But if you're using the dynamic programming solution, it actually doesn't change that much. Again, because you've memoized, so you already know how many pieces there are, or you can already solve parts of it and not have to resolve those parts. And the problem itself doesn't change. So what does part 2 look like? I basically just call this expand method. You can see the difference here between this map and this map is I call the expand method on the record set. And what does that expand do? Basically, I just take the springs and create an iterator and cycle it until I get 5 times of what I'm expecting. And I do the same thing for the growths. I take an iter of the groups, I cycle it, and then I only keep 5 times the number of groups, right? So both of them are like 5 times as large. Now I can solve the same problem. But the solution itself, the possible solutions function, doesn't change, right? I just now have a bigger record that I'm starting with. I'm still going to decompose it. I'm still going to check my sentinel cases where like, oh, I have an empty group, or I don't have enough room to fill all the groups. And then I'm still going to see like, okay, well, how many do I get if I place it here? And how many do I get if I don't place it here? And that the sum of those two is the number of solutions for each of those problems. And that bubbles up until you finally get the whole record set, which now has all of the solutions in it. I just wanted to show you too, here I ran it. I added some timings here. You can see like it does increase the time, but not that much. And I also, if you want to look, I wanted to track the number of memo hits that I got. How many times did I find a solution that I've already found and not have to redo it? And so I kind of I use this like once lock feature. It's a newer feature in Rust that allows you to like keep a static value. And basically what I do is every time I get a memo hit, I update my count there. So that will tell me, then I can, in my solutions, I can print out how many memo hits I actually got. And so you can see for part 1, I got 3,900 hits. For part 2, I got 70K hits. And that number is really big, which is good, right? But it actually doesn't express like how much time that saved, because some of those hits are like substantially larger in computation than other hits, right? If you're at the very end, you're probably hitting those many times. But once you're near the top, if you've already seen a partial solution near the top, that saves you a ton of recursion and a ton of time of how deep you go. So I just wanted to include that there so you can actually see how much memoization helps. If I did this without memo, it may not ever finish. In fact, we can check it. Maybe I can try and run it. I basically just do like this right here and run it again. This like may never, you can see this one still runs pretty fast. It's about twice as slow, but this may never finish. It just, you can see it's still not done. The idea is, I'm doing a lot of branching. I'm doing a lot of breaking up into subproblems, but now I have to like recalculate some of those subproblems, right? There's some section here in the tree, it actually looks like this, that is the same as a section over here, and there's no reason for me to calculate that twice. You can see it's still not finishing, right? So, if I run it again, now it runs super fast, right? And this is some large number, but I hope all of this is to illustrate how cool dynamic programming is and how cool memoization within dynamic programming is. Again, memoization is just one way to help with dynamic programming. You can think about more generally, as I've said before, dynamic programming is how do I decompose a problem into smaller problems and then solve those smaller problems. One way that you optimize it is through memoization. Another way is using tables. You'll often see some solutions use tables, which is basically just, it's more helpful when you're using like numbers or whatever. But the idea is you may have like a 2D or a 3D table, and you just kind of track results, and you can use those results to help you solve problems higher up the chain, right? All of them basically go to the idea of memoization. If you've already solved or you know the solution to a previous set, you can just reuse that to help you get to a better place. Okay, so again, that was it for day 12. It was a dynamic programming problem. If you've done dynamic programming before, you could get to it. It did take me a lot of time to get the right values right here. I think I mentioned it earlier. I spent a lot of time, I got stuck on this end piece right here and recognizing, at first I was just checking, or I wasn't even checking this part right here. I was just assuming that I could get to the point I needed. If I could place it there, I was okay. And it was then later I realized, oh no, if there's a damaged piece after my group, I can't place it there. Then I ran into a stack plate trace where I was like, oh, well, it may be damaged, or I may be at the end, right? If I'm at the end, I can't check for that next piece, and so that took me a little bit of time to figure that out. and get to that point. But it also, it took me time to, you can see I made a lot of comments here. Sometimes that's what I do when I'm working on these like dynamic programming or recursion problems. It helps me to like make comments at like a very high level before I actually write the code, right? I know that my Sentinel cases are check if we've already calculated it, check if there's no groups left, check if, I have enough space to solve the rest of the problem, and, check if I'm operational. These are all my Sentinel cases up there. You can see I have a lot of comments here because these were the things I'm thinking about. And like I'm like writing it out in my head, or I'm thinking it out in my mind and writing it out here to get to that point. So I don't want you to by any means think like, oh, I'm a pro or something like that. So maybe some people solve this in 2 minutes or whatever. I haven't looked at the leaderboards, but it did take a few minutes to like think through all of the different cases, right? It took some time. And I spent some time debugging because a lot of the cases are very specific, and you need to think about like where you are in the string and how far along you are, and how the solutions, the number of solutions bubble up to a total solution. So again, if you're not familiar with dynamic programming, check this out, or maybe find some other places. If you want me to do some videos on dynamic programming where we like solve these problems, or we talk higher level about how to do dynamic programming in general, I'd be happy to do those. I would love to see your comments. Maybe you solved it some other way. To me, it looked like a dynamic programming problem. Maybe after this video, I'll go check and see other solutions and see if they did it different ways. But if you found some other faster solution, or for example, if you know about nonograms, I hope I'm saying that right, and you happen to use like some existing nonogram solver to help you get there, that would be really cool. I'd like to see that because I do think there's some relation here, and it would be interesting to like delve into that further. I just don't know if I have time to do that. But if you happen to do it that way, I'd love to see it. I'm also always welcome to hear your input. If some of this stuff doesn't make sense, let me know. I'll try and explain it further. Or if there's optimizations I could do, places I could do it better, let me know. I'm always looking to improve or looking to understand better. That's what programming is about, right? It's a tool, it's a skill. It's you get better at it by practicing it, and I have fun practicing it with these puzzles. So talk to y'all later.